Okay. And we're going to look for something called improper integrals. We're going to start first with what we call the infinite intervals here. So infinite intervals, let me go back to the iPad. So you're going to have an integral that looks like this, maybe from a to infinity. Fx dx, that's one type. Negative infinity up to b, that's a second type. And then you're going to have something like this. You're going to have negative infinity to infinity, and we forgot our dx, these types. So these are all known as infinite intervals. So why do you think they call it infinite intervals? Why do you think they call it that? What is this? Infinity, is that true? So you say, and also, what is this? Negative infinity. What else do you have? Negative infinity to infinity. Note, in the past, you just had what's called a finite interval, meaning your function was over this closed bounded interval. This is called a finite interval, meaning numbers. Infinite is what we're looking at now. Okay? And so I'll give you first the definition, and we have to look at it in what's called cases, right? Or types. So what I have here in my notes and in your book under improper integrals, if you have something from a now to infinity, okay, I'm going to define for you guys what that means, and that's even defined in my notes here in the browser there, okay? So what we're going to now do is you're going to do this. You're going to actually go, you're going to integrate from a to t now. So you're going to replace infinity with a dummy variable t, okay? And you're going to integrate that. So let me go back to the iPad, and here's to tell you what I'm saying. That infinity gets replaced now with the idea that limit as t goes to infinity. We're going to take a limit now. Okay? There's your t. T is going to infinity. So that whole portion really turns us into two things, a limit and an integral. I call this here a lot of times I of t. So you have to know how to integrate. Okay, that's I of t. And what I also want to say is that what else is going on here? I think in my definition, if we go back to the browser, okay, yeah, we'll go through all that kind of, I guess. You know, this relationship, yeah, a is smaller than t, by the way. But this is your definition of your first improper integral, and we call that sometimes case 1. So you have to do a whole bunch of case 1 examples. And I want to kind of share with you guys an idea here, okay? Like if you have a curve that looks like this. Here's my F curve. And the improper integral, if you remember this area under the curve, okay? This is going from really a to what? Infinity. Here's our function. And you remember you said, okay, remember that approximating rectangle, you know, back in calculus 1, you get this area under the curve, but then now my interval is not finite, it's now infinite. So that's kind of what they're talking about, okay? You guys okay with that? But if you said, what if they change this now from a, right? You can integrate now from not a to infinity, but a really up to some value, what? T now, okay? And so now, this is what we're calling I of t. The integral in terms of t. And I guess I'll change the color so it makes some sense. But that's kind of what we're looking at. Okay, so this is my I of t, and you say, okay, what do we do once we find that kind of area in some sense? Well, you know, we let that t now go to infinity, and then because this is a limit question, we have two ideas. Okay, this is a limit. What do we guys know about limits? They either converge to a finite value or they what? Diverge. It's called divergence, either converge or diverge. So what's going to happen now is, since this whole thing is a limit, we're going to have this idea called convergence and divergence. And I'm going to share with you guys what that is as we go through some examples. Okay? But the first thing is you have to know how to do some what? Integration here. Okay? So if they say, can you integrate from 1 to infinity here? X over, let's say x squared plus 2 squared dx. Okay? It's an improper integral. By definition, this is the limit now as t goes to infinity, 1 to t, and we have to integrate this. So then the question is going to be now the following. Okay, this whole thing is my I of t. So in other words, I have to integrate this in terms of this variable here. It's going to be an I of t function because t is a variable, right? You replace that here. This is that t there. So it's going to be an integral in terms of t, the answer, a function of time. That's all they're saying. So then the real issue is going to be this. Does I of t go to infinity, or does I of t go to some finite value, I don't know, c? It's finite. So is the answer finite, or is the answer what? Infinite. Okay, you guys see what I'm saying? Either that limit's going to be infinite because it's a limit at infinity. So that either is going to go to infinity, or it's going to go to some finite number. Okay, you guys with me on that? Because it's a limit question now after you integrate. So it's two things. Integrate and then get the limit. So that's what you're doing. And so that's kind of analogous to the area under the curve being finite or being infinite. Okay, does it explode or does it become finite? Can you get that area? So that's going to be the question. Okay, you guys okay with that? So let's find the integral. Say, okay, so what I kind of do is I'll say I of t now becomes what? Let's integrate from 1 to the variable t, x over x squared plus 2 squared dx. How would you guys integrate this, by the way? What do you guys think? What's the integral for this? Anybody know how you would integrate? How would you integrate x over x squared plus 2 squared? What would you use? You're going to use u sub. Is that true? What is u? X squared plus 2. Then du becomes 2x dx, or really dx is du over 2. So what's really going to happen is you integrate from 1 to t, x over u squared du over 2, I think it's 2x. Sorry. Okay? And then sure enough, what happens? Right? Your x cancels. So this integral becomes, if I pull out the constant, 1/2, that's u to the minus 2 du, which would be 1/2 u to the minus 1 over negative 1 from 1 to t. It's negative 1 over 2u from 1 to t. So that's negative 1 over 2t plus 1/2 I of t now 1/2 minus 1 over 2t. Okay, you guys see what I'm saying? So this is my integral in terms of t, and that's why I say this is kind of that, it's a t function now, right? This is I of t now. So this is what I found here. We're going to call this the whole thing I of t. So you say to me, well, aren't I supposed to, by definition, take now the limit as t goes to infinity, 1/2 minus 1 over 2t. Okay?
Excuse me, Professor, do we need to change the upper limit and the lower limit because we use a U sub?
No, just keep it, do it exactly how I did it here. Keep it, I mean, you have a good point. Let me put it this way. I apologize here. Oh, I think we forgot x squared plus 2. Is that right? I apologize. Oh, well, let's go back. You made a mistake. Good job. I apologize. I'm doing two things at once. Reading an email and thinking and going through that. Let me apologize to you guys here. Okay? What was u anyway? You guys remember what u is? This is u. Is that true? So here's what I'm going to say to you guys. Put the u back, x squared plus 2. So this is minus 1 over 2 x squared plus 2. You can evaluate that from 1 to t. Now you can say negative 1 over 2 t squared plus 2. Really plus 1, well, yeah, plus 1 half 1 squared plus 2. Which is going to be, is that 1/6? Let me double check. Wasn't u x squared plus what? 2? Okay. T squared plus 2. Well, 1/6? 1/6 minus 1 over what? 2. T squared plus 2. So I apologize for that. Now we're going to take the limit. So we're going to get rid of this. So that's really now going to be the limit now of that. So we say we're going to take now the limit. T goes to infinity. 1/6 minus 1/2 t squared plus 2. Okay, that looks a little bit better. Okay. So here's what's going to happen now. What's this limit? In other words, I of t goes to what? Does anybody know? 1/6. Outstanding. As t goes to infinity. Okay? So that integral goes to 1/6. This is a limit. Do you guys know what we say about this? This number here that we just got, that is called a finite number. 1/6 is just a number. And so the integral here, this integral, since it's really a limit, goes to 1/6. So that equals what? 1/6. And this is what we say, since that's finite, ladies and gentlemen. We say the improper integral converges. Okay, because it's finite. And we often write it this way symbolically. Okay, so if you look in your book, you know, we simply say that that number is less than infinity. This is the notation for saying that it converges. So a lot of times you'll see that. We'll see that in the notes here. You say, oh, is that why the notation is this? Yes, that's what we're looking for. This integral converges if it exists, if it's finite. Goes to a number. And what can happen, it doesn't have to go to a number. And if it doesn't go to a number, if that limit is really big, it's infinite, then we say it diverges. And there's a very simple way to show that as an example. I can kind of make this up. So say, oh, okay, I'm going to integrate now, ladies and gentlemen, from maybe 4 to infinity of maybe x squared plus 2, okay, dx. We're going to see why this integral is going to diverge, all right? So here's what happens. We write it as the limit as t goes to infinity. We integrate from 4 to infinity. I'm sorry, from 4 to t, because we replace infinity with t, x squared plus 2 dx. So this is the definition of your improper integral. This is that I of t. One third x cubed plus 2x, 4 to t. So you say, what does that give you? Well, that gives you what? 1/3 t cubed plus 2t minus 1/3 4 cubed minus 2 times 4. Okay? So we get 1/3 t cubed minus 2t minus 64 over 3 plus 8. Okay? And we don't have to add those numbers right now. And I think that was plus. That was not minus. Okay? So this is what I of t is when I integrate it. So what do you guys do now by definition? What do you guys think you have to do? Take the limit as t goes to infinity of that I of t, which is the limit, t goes to infinity now, of 1/3 t cubed plus 2t, yes, minus the arithmetic, but you guys are going to see what I'm talking about, okay? So what do you guys think this goes to? if t is getting big, right over here, t is getting big, right? What's going on here? And here. Isn't it getting bigger? Because it's t cubed and then plus 2t. So what do you think this means about my I of t now? I of t goes to what? Infinity. Good. As t goes to infinity. So it gets just too big. Yes?
Can you maximize the
Make it bigger?
whole T?
So,
Oh, no, the
oh, I'm sorry. Like something like this? We could do that, or I can go to this. So you can see better? You can see a little better? Okay, I apologize. You're welcome. All right. So what we want to now go and say is this. This equals now what? Infinity. And you say, what does that happen if this is infinity, right? What does that even mean? What that means, ladies and gentlemen, is this improper integral. If we go from a to infinity, this integral, if it equals infinity, we say it diverges. So there's going to be two answers. Either it converges, goes to a finite number, or it diverges, goes to infinity. And that's essentially what we're looking for. Okay? And essentially what you're saying is that the area under this curve then explodes. And that should make sense. In other words, you guys know something about this. I just want to remark here. You guys know how that curve looks, by the way, this particular curve? X squared plus 2. That's a parabola that opens up. So I want to say something about this so that you guys are aware. If this is 2, this is y equals x squared plus 2. Now, if we go from 4, if we say this is 4 to infinity now, what do you guys know about this area here? If we have an approximating rectangle somewhere, isn't that area going to get what? Bigger and bigger? In other words, isn't that length getting bigger, bigger, and bigger? So the area under this curve is getting to what? Too big. So that's going to be a particular issue, ladies and gentlemen. So these are kind of some fundamental examples of case 1 here, so you guys know. So we can see very easily that the area under the curve is going to get too big if we use that function. Compared to a function like this that may be decreasing, I just want you guys to note something here. If I say, can we integrate this function, 1 over x dx. Let's be careful here. Here's a nice, simple example. This curve goes like this as we what? Go from 1 to infinity, right? So if you look at this situation, you go, oh, this is a nice situation. Well, what do you guys know about the area under this curve? Well, you would think it's going to be finite. Is that true? Because what's going on with that approximating rectangle again? It's getting smaller and smaller and smaller. So the areas here, when you add them up, you think is going to get smaller, smaller, and smaller for those rectangles. We think that it's going to be finite. But if we use the definition and we say this is the limit now as t goes to 1, integral from 1 to t, 1 over x dx. Okay, here's my I of t. What does that become? Is that natural log absolute value of x? We integrate from what? 1 to t. Okay. And then, I mean, we can actually keep the notation. That's not a real problem. Isn't that the natural log of t minus the natural log of 1? Because those values are positive. And that's 0. So this question becomes the limit as t goes to 1, natural log of t. Is that right? You guys with me on this? Where does that limit go to? And I made a mistake. That's not t goes to 1. T goes to what? Infinity. I'm thinking of another improper integral. Not today. Not today. Okay. Does anybody know, what does this limit go to? What does this equal? Does that go to infinity? How do you guys know that goes to infinity? Didn't we do those like the first week? And that curve increase forever? So what we showed here, that this integral, yes, equals infinity, and that means the improper integral diverges here. So you might say, Mr. Judge, what's your point? Well, just because you have a decreasing function and you think that area is going to what? What's the area going to do? It's going to be finite, right? That's not a guarantee. And I know that's counterintuitive, but there's actually a lot more to the story. Because 1 over x, if I go to Desmos, let me share with you guys something in Desmos. Where are you, Desmos? Here we go. Yes, 1 over x, I say y equals 1 divided by x. That's a decreasing function. And then I'm going to show you guys that this function here, y equals 1 divided by x squared, that's another decreasing function. But what do you guys know about the blue curve compared to the red curve? Starting at the interval 1 to infinity. The blue curve is going to get to the x-axis faster than the what? Red curve. Does that kind of look interesting to you guys? Right? Do you guys see what I'm saying? It turns out what really happens, what this is about, if you have decreasing functions, functions that decrease and get to the x-axis fast, whatever that even means, fast enough, will be convergent. If it gets to the x-axis slow, will be divergent. So what I'm about to show with you guys here, or share with you, and every book kind of talks about this in calculus. Like every book will show you this kind of, we'll compare these two examples. Go, let's integrate from 1 to infinity now. 1 over what? X squared dx. You're going to find that this actually converges. And if I raise the power to 3 or 4 or so on, it'll converge. Now, definition, what does that mean? The limit t goes to infinity, we integrate from 1 to t, 1 over x squared dx. What is this? I of what? T. So if I want to find what that is, I say, okay, integrate from, let's find out what that is. Is that negative 1 over x from 1 to t? negative 1 over t minus negative 1 over 1, which really becomes 1 minus 1 over t, so you guys know. So that's your I of t. If you take the limit now as t goes to infinity, what do you get? This equals what? 1. Easy peasy lemon squeezy. That integral is 1 here. Now, you know that this number is what? Smaller than infinity. So what we're saying is ultimately this integral is going to do some what? This is smaller than infinity. This means we have some what? We have converges. So what I'm sharing with you guys is the fastest you get to the x-axis, if you get to that x-axis fast, whatever that means, it's going to converge. So don't think because it's a decreasing function, it always converges. That's not the case. It has to get to that place fast. And we'll look at this in green. What do you guys think about x cubed? Doesn't it get there even faster than the blue function? From 1 to infinity? It's even faster, isn't it? So if I'm increasing the power, just so you know, I get there really fast now. So the area is going to be finite. How can you prove it? Do the improper integral. So essentially, and I'm looking at some of these kind of examples. Not all of these examples, ladies and gentlemen, are kind of this easy. But you have to start with some of these here. And I have a whole bunch, really. So that page I have for you guys has a whole bunch of extra other examples that you may want to consider because, you know, it really comes down to can you integrate and then take a limit. Okay, you guys okay with that? And so let me give you guys something else here. 0 to infinity. 1 over x squared plus 3x plus 2 dx. You go, oh my God, you're throwing me to the wolves already, right? What do I mean by going to the wolves? What's this? What's the definition? Limit t goes to infinity, 0 to t, 1 over x squared, sorry, plus 3x plus 2. Okay, here we go. When you factor this, isn't this what? X plus what? 2? X plus 1. Is that true? You guys okay with that? Now, you don't know this yet, but you will. This has vertical. Well, you do know this from Calculus 1, from pre-calculus. Where are your vertical asymptotes? X is negative 2. X is negative 1. Is that right? Vertical asymptotes. You guys okay with this one? So is it okay for this interval? This interval goes from 0 to what? It's 0 to infinity, but in this picture, it's 0 to t, where t is bigger than 0, by the way. So 0 will be bigger than t. The point I'm making is we don't have to worry about those vertical asymptotes, just so you guys know. But how do you guys integrate this function here? Yes. You're going to have to use what? Partial fraction decomposition. So even though these questions, some of them look very easy, they might throw you to the wolves there, meaning they assume you could do partial fraction decomposition. They assume you know how to do that. Now, by PFD, I can tell you essentially what you're going to end up with. Okay? So this is by PFD. I of t is going to end up equal to this. You're going to integrate 1 over x plus 1 minus 1 over x plus 2 dx. You'll get this by partial fraction decomposition. So this is the natural log absolute value of x plus 1 minus natural log absolute value of x plus 2, which is natural log absolute value x plus 1 over x minus 2. And you have to evaluate this from 0 to what? T. So you know what you end up with? If you plug in those things, you get natural log t plus 1 t minus 2 minus natural log of 1/2. If you plug in the 0, it's plus t plus 2. Okay, so here's going to be my question now. Now you say, Mr. Judge, how come I got rid of my absolute values? What do you guys know about t? This is from 0 to t. T is positive, is that right? So I want you guys to know my t here is positive, which means when I plug in this t and this is plus, you know, I can get rid of the absolute value because what's inside there is positive. But then, what do I have to do? We have to take the limit. In other words, what happens as t goes to infinity? You're looking at limit. T goes to infinity. Natural log t plus 1, t plus 2 minus natural log 1/2. Okay? The real question is what happens here? So I want you guys to look at this and say, okay, as t gets big, where does t plus 1 over t plus 2 go to? So you're going to have to find, where is this going to? Does anybody know where that goes to? Be careful. Anybody know where that goes to? I wish I had my sound effects. I know half of you guys can't even see me. Where does that go to? Okay, and then what does that equal? Yes. Good job. Why is that 1? You guys remember something called L'Hopital's rule? Because in red, isn't that really the limit here? T plus 1 over T plus 2. And that's why you're saying, oh, that's improper. Or I'm sorry, that's an indeterminate quotient. So by L'Hopital's rule, that limit, as t gets big, what's the derivative of t? 1. What's the derivative of t? 1. What's the limit of 1? Well, that's 1. So yes, you did use L'Hopital's rule, but that's this limit here. What's next? What's the limit of the natural log now?
0.
This goes to, ladies and gentlemen, this goes to 0. So that means the natural log here of t plus 1 over t plus 2, that goes to 0. So this thing goes to what? 0. This is a constant, which goes to really natural log of 2. Does anybody know why it's natural log 2? It's really minus natural log of 1/2. But by properties, that's natural log of 1/2 to the negative 1 power, which is natural log here of 2. And that's a nice finite what? Number. The natural log of 2 is finite. So that means this thing converges, ladies and gentlemen. Converges. So I'm sharing with you guys some kinds of problems here that are called case 1. This is going to be, and I'll let you guys copy that note there, but this is kind of how you go approach some of these questions. They're going to test. Hey, do you know L'Hopital's rule? Can you know partial fraction decomposition? You guys see what I mean? I guess they want you to study your past homework. Oh my God, I got to do my homework now? Really? Yeah. Can I wait till the night before? No. What do you do the night before? Sleep. Good.
Professor, I think we also can use the numerator and denominator both divided by t.
Yeah. Yes, you could use the calculus 1 approach. Yes, you could do it by calculus 1. Anyway. Okay. Okay, how about this? 0 to infinity, ladies and gentlemen. Cosine squared theta d theta. Say the limit t goes to infinity. Integrate 0 to t. Cosine squared theta d theta. So we want to know, this is going to be that I of t. So my integral here from 0 to t, cosine squared theta d theta, you guys know, that's going to be the integral from what? 1/2 1. Isn't that 1 plus what? Cosine 2 theta? Is that right? All right, what do you guys get here? You guys know? That 1/2 theta now, okay, plus 1/4 sine 2 theta. And we're going to integrate this from 0 to t. So what do you get now? That's going to be what? 1/2 t plus 1/4 sine 2t minus 1/2 times 0 plus 1/4 sine really 2 times 0. In other words, this whole portion goes to 0. Okay? And so I of t now is 1/2 t 1/4 sine 2t. So what happens now as t goes to infinity? Where does I of t go to? What? In other words, aren't you taking now that limit here as t goes to infinity? So do you guys know something here? You're gonna have an issue here. Okay, where is I of t going? Why does this thing go to infinity? Anybody know? Why is that end behavior infinity? Let me do this. 1/2 t. Let's do this here. Y equals 1 divided by 2. I guess I have to do x, not t, plus anybody happen to know why this is happening? You see that there? This function? What happens is this, I know that's x and not t, but it's the same kind of question. In other words, what's the end behavior of this function as x gets big? Because that's kind of like as t gets big. What do you guys think the end behavior is? What's that going to be? That's infinity. So why do I know that analytically? Because isn't this portion here getting big? Say yes. How do you guys know? T's getting big, so 1/2 t is getting big. Is that right? And then what are you guys adding here? In other words, note what's going on with the limit as t goes to infinity for 1/4 sine 2t. There's a problem with this, right? Sine 2t, what's going on? Oscillates between what? Plus or minus 1. Is that true? As t's getting big, sine 2t, it's going to oscillate between plus or minus 1. So you say, but I have 1/4 that. Okay, pull out your constant here. So now, maybe you say, I can talk about that sine oscillating. But the whole thing is oscillating now between what? Plus or minus 1/4. So you're adding 1/4, subtracting 1/4. Is that true? So if you said this is getting big, plus or minus 1/4, isn't that still getting what? Big? So the problem with the sine and even cosine is going to be that it's going to oscillate between two numbers as t gets big. And so big plus this small plus or minus 1/4 is still getting what? Big. So this limit is what I'm saying. The limit of this goes to infinity. And that's what we just said, which means your integral diverges here. Okay? That's infinity. This diverges. All right? You guys okay with that? And we can verify that with the graph so you guys know that end behavior. Because as going to infinity is end behavior. You know? And then the case 2, you say, what about the definition of case 2 now? Well, it's very similar. You say, what do I mean? Well, this is going to be the limit now for case 2. I guess I kept it in black. T goes to minus infinity. We're going to go from t to b. Okay? So now replace your t with that minus infinity here and make that a limit, and I just want to make it a little nicer. So if you guys can see that, that's called case 2. And that's your t, the lower limit. Okay, you guys okay with that? It's called case 2. So I'll give you an example here, kind of a nice example. Negative infinity to 0, x, e to the x dx. A case 2 question. So we're going to write this now. You're going to use the definition. Say, what's my definition? That's the limit. T goes now to minus infinity. We integrate now from t to 0, x, ex, dx. So you're going to need this. What do you guys use now? Integration by parts. And then if you actually have memorized some of the integrals, is that okay? What is that going to be, right? You guys remember that? Isn't that x, e to the x minus e to the x, 0 to t. So it's 0, e to the 0 minus e to the 0 minus t, e to the t minus e to the t now. So this is negative 1 minus t, e to the t plus e to the t. So I'm going to rewrite that. That's I of t is going to be what? E to the t minus t, e to the t minus 1, I of t. So what do you have to do with this integral? You have to now take the what? Do you have to take the limit? T goes to minus infinity. Okay, what's this limit going to be? Does anybody know what this limit's going to be? Isn't limit of a what? Sum and difference. Okay, t e to the t minus the limit of 1. Is that right? You guys okay with this? Anybody know where this limit goes to? Where is this going to? Good. Where does this go to? Isn't that 1 because it's a constant? And then what about right in the middle? Where is that limit going to? I think that's negative infinity times 0. Is that right? Is that true? What is this known as? Indeterminate what? Product. Is that right? Remember from that homework, indeterminate product? So if that's an indeterminate product, what do you guys have to use? Well, you have to fix it. Is that right? So what's your fix? I'm going to put t over 1 over e to the t. That's the fix, which is t over e to the minus t. So when you take that limit via the algebraic fix, we get negative infinity over what? This is the decay curve over positive infinity. Okay, you guys know what I'm saying? This is from your homework from L'Hopital's rule. Did you start that yet? Hopefully. Good job. Now, what do you guys use then? By L'Hopital's rule, what do you guys use? Isn't that 1 over minus e to the minus t? Is that true by L'Hopital's rule and chain rule in the denominator? And you go, well, what is this going to equal? That's a limit. T goes to minus infinity. And then it's just minus e to the t. Is that right? So what is this limit? E to the t. Isn't that a growth curve? I think this is going to be what now? What does that equal? Is that negative 1 times 0, which is 0? I think that limit is 0. Double check, ladies and gentlemen. I'm not awake and I'm multitasking. And so this portion is 0, too. So at the end of the day, what do you think this limit is going to be? Your first case 2. Does anybody know? What is that going to equal? This equals negative 1. Is that true? So that's negative 1. What do you guys know about negative 1? Is that a nice finite number? Say yes, that's less than infinity. So we have what? This converges. So we have a convergent improper integral. All right, you guys want to see an example of a divergent? Case 2. I can sketch it for you, sort of. This is going to be e to the minus 2x dx. So this will be the limit. T goes to minus infinity. Reintegrate from t to negative 1 e to the minus 2x dx. Now what is this? This is what? I of t. T. Negative 1 e to the minus what? 2x dx. Okay, you guys okay with that one? So here's the thing. How do you guys do this? This is u is minus 2x. So you're going to use u what? U sub. And of course, du would be minus 2 dx, or dx will be du over negative 2. So this integral ultimately will become, ladies and gentlemen, negative 1/2 integral e to the u du, which is negative 1/2 e to the u, or negative 1/2 e to the minus 2x. We integrate from t to what? Negative 1, which will be negative 1/2 e squared plus 1/2 e to the minus 2t. So double check this, ladies and gentlemen. My arithmetic is okay. I of t. Now, this means that the limit t goes to minus infinity, 1/2 e to the minus 2t will be minus 1/2 what? E squared. So do you guys know where this first portion goes? Where does this go to? Do you guys know that e to the minus 2t will go to 0 as what? T goes to minus infinity, right? Because isn't that a decay curve? Let me double check. Is that true? I don't think that's true. Where does this go to? That doesn't go to 0. Where does it go to? Doesn't that go to infinity? That's decay. How do I know? Isn't that a decay curve? Yes. So if t is going to minus infinity, that goes to positive infinity. So what does that infinity minus a constant become? This equals what? This is infinity. Is that true? So, ladies and gentlemen, what we've shown is this integral diverges because this equals infinity here. So what do we say? Diverges. What do you guys think about this? Easy peasy lemon squeezy? Let me take a look, though. This is calculus 2. I think in assignment number, what, 2? Yeah, we have some improper integral homework. So you guys can get started on some improper integral homework. As you guys can see, essentially it's using your definitions. And what does that mean now? Do you guys know? You should know how to integrate, and then you look at the limit. So this is putting those two ideas together. It's that simple. Anybody have any questions on that? What section is that? You guys know what section that is? It's 8.8. All right. I told you guys there's work in calculus 2. Okay, we'll see you guys later. I hope you guys enjoy the the streaming that's somewhat back, but it's recorded and it's online, and we'll see you guys later. By the way, if you want to see additional examples, do they exist? Let me go back here so you guys know. Where do the additional examples exist? If I go to the browser here. Okay, let's go to the browser. Okay? Browser, where are you, browser? Browser. Where are Okay, ladies and gentlemen, good afternoon to you guys. I think we're good here. Looks like it worked. All right, let's see who we have. All right, we got a few, 9 people online. Okay, wow. Ladies and gentlemen, good afternoon. 9 online. Okay, I think we're good. We're going to continue, here. Ladies and gentlemen. We're going to look at. If I go back here to the browser now. All right, we got a few, 9 people online. The browser, okay, ladies and gentlemen. Good afternoon. 9 online. Okay, I think we're good. We're going to continue, ladies and gentlemen. We're going to look at. If I go back here to the browser now. All right, we got a few, 9 people online. The browser, ladies and gentlemen. Good afternoon. 9 online. Okay, we're going to continue, ladies and gentlemen. We're going to look at. So here is yesterday. If I go back the work we started. The browser now. All right, we got a copy. A few, 9 people online. The browser, ladies and gentlemen. Look at is 9 online. Okay, we're going to continue, ladies and gentlemen. We're going to look at. So here is yesterday. If I go back the work we started. The browser now. What's going on? Hold on. A few, 9 people online. The browser, ladies and gentlemen. Let's get rid of that. Sorry about that. There was an echo. Okay, we're going to look at case number 3 in case you guys can't see there. I got rid of the echo now. Anyway, okay, so here's really what's going on in case number 3 now. You can have an integral from negative infinity to positive infinity. Okay? Now, it's going to be very, very simple in the sense that you're going to separate that integral over 2 intervals here. Zero to infinity. And you really could pick any number here. So I would say to you, generally speaking, this is really a C value. This is a C value. So you're going to split that up into 2 improper integrals. Okay, so yesterday we called this like case 2 or something. And this one we started with was case 1. So, ladies and gentlemen, there you go. This is going to be known as overall case number 3 in our notes. So, case 3 in your notes is these sums. Now, in order to get convergence, here's what we have to note. This is extremely important. This thing is finite. In other words, the integral converges if both of these 2 integrals converge. So this one has to converge, and this other integral needs to converge. So they both need to converge because you're talking about a finite number, right? Has to be finite. So this is what I'm saying. In order to get convergence, you need both of these. This is an and. Okay, because it's like saying a finite number plus another finite number will simply give you a finite number, right? N plus n. If one of these is infinite, and here's the problem, just be careful. You say, what do you mean be careful? If one of them, I'll say, by the way, okay, if one of them actually, whether it's the first one or the second one, if this actually happens, then, or I'll say this or this. If they are divergent, either of them, this is an or statement. If either are divergent, then the whole improper integral over the whole real number line is divergent. So remember, this means what? This divergent, or if this diverge, or even both, but nevertheless, that means the overall diverges. So I want people to really understand that important detail. Okay? So this is equal to infinity. That means divergent, divergent. This is less than, so that means convergent. Okay? So if both integrals converge, then over the real number line, because that's what this is. This interval that we're talking about is over the real number line, all real numbers here. Okay, you guys see what I'm saying here? That's what's going on there. Anyway, so let's see an example here, and we can pull out some examples. I have one here that I'm looking at. X e to the minus x squared dx. And so right away, I would suggest split this up into 2 integrals. I always let my c value be 0 if it's available. It is. And I shouldn't say that. It's always available. Because 0 is always available in this real number line. So my personal choice always is to use that 0. Okay, so this is an integral now over all real numbers, right? Because that's going to be from minus infinity to infinity. This is what we're saying. So you split it up into two improper integrals. And if you pick one, and here's the good news, it doesn't matter which one you pick, start somewhere. I'm going to start with a case 1. That's a limit. T goes to infinity, 0 to t. So focus on this part first. Remember, this is a nice improper integral. This is that I of t. So, ladies and gentlemen, for this I of t, tell me here, what would you guys do? How do you integrate this? U what? U sub, and u would be minus x squared. So, du minus 2x dx. Dx will be du minus 2x. So we got to integrate x. That's e to the u du over minus 2x. So yes, your x goes away. So now you have really negative 1/2 integral e to the u du. Okay, hard to say. That's integral e to the u. U here is minus x squared, and we go from 0 to t. Minus 1/2 e to the minus t squared, and then that's going to be at minus the minus. Okay, so e to the minus at 0 squared. 1/2 minus 1/2 e to the minus t squared. Here's your I of t. So you want to now take the what? Take the limit. What are you guys taking the limit of? T goes to infinity. So what happens as t goes to infinity, right? You can say as t, we'll put that in red, the limit. So as t gets big, where does this I of t go to? Do you guys know? That goes to what? 1/2. Is that true? Right? You guys okay with that one? Does that go to 1/2? Why does that go to 1/2? Yeah, this portion here goes to 0, doesn't it? Doesn't that go to 0? As t gets big? See, why does it go to 0? That's a decay curve. It's decay, e to the minus t squared. So if t gets big, that's e to the minus like 5,000. This whole thing will go to 0. So anyway, just to kind of demonstrate to you guys that, so you guys know. So that means that this, where is it? There, where is it? That means that this integral, this converges to the finite value 1/2. So what that now says, since you have convergence, you're going to have to find whether or not this other one converges. Because in order for this real number line case 3 to converge, remember, we need what? Both have to converge. Both integrals must be finite. They have to converge. If not, if you have at least one, then that means it's divergent. So okay, you say, well, how do I do this integral? Well, same way, but that's the limit now. T goes to minus infinity. T0x e to the minus x squared dx now. So that is what we got to focus on. Okay, and then you might say, but is that the same integral? Yes, it is. Isn't that the same integral to do? I think that was purple. your I of t just has different limits. So what'd you get here? This is minus 1/2 e to the minus what? T squared. And we're going to get that from t to 0, which is going to be negative 1/2 e to the minus 0 squared minus the negative 1/2 e to the minus, let me go back. Sorry. That should be an x. Oh, come on. Let's get should be an x squared. Let's double check. Yeah. All right, so this would be minus t squared, I think. Huh, why is that going to be, okay. Negative 1/2 plus what? 1/2 e to the minus t squared. So double check, ladies and gentlemen. Double check if we have our signs okay. I think so. Bless you. And then, if this is my I of t now, what's the limit of this now? Remember? Got to take the limit. So we say st gets what? Big. I of t goes to negative 1/2. So you say, what is going on here? So if we didn't make a mistake, they're both finite. But what's the final answer? Huh? You know what that equals? That's 0. Could that be 0? That looks like this integral is 0. Negative 1/2 plus 1/2. Because we have those two answers here, right? That's 0. So x e to the minus x squared. So let me do something here. Let's look at Desmos. And I want to change the color. That's e. I think it's exponential. That's going to be minus x squared. Okay. Okay, that's what I suspected. What do you guys think that means? Remember, area to the right is all those approximating rectangles. Area to the right is 0. You guys see that there? That area we just seen from 0 to infinity is 1/2. So we just actually computed that. You guys okay with that? What's the other area? Negative values. That's negative 1/2. This curve is symmetric. Is that right? Looks like it's an odd function. Symmetric about the origin. So that looks pretty right to me. What do you guys think? Does that look like it makes some sense? So over the all real number line, the area under the curve, because to the left, you have those negative approximating rectangles. To the right, you have the positive approximating rectangles. So altogether, that's going to be 0. So yeah, it makes a lot of sense. All right. Anyway. Good, good, good. I like that. Okay. Now, you might say, however, what if I get something like this? Negative infinity to infinity. X squared, 9 plus x to the 6 dx. Right, you might say, is that going to be, again, negative infinity to infinity? I'm sorry. How do you want to look at this? We're gonna do it the way it was defined, okay? Negative infinity up to 0. Remember, that's my favorite number to use. 9 plus x to the 6 dx. And then 0 to infinity. Now, I want you guys to pay a quick attention to this function here, because we're going to use, like, for example, the last example here, the function they gave us was what? Did you guys notice? This is an odd function, by the way. And more than that, this is thought of as a symmetric interval. So does anybody remember from Calculus 1, maybe? Just put a note. You had, I think I gave students this fact here. This equals 0. If what? If f is odd. Is that true? Case 1. Case 2. This function is 2 integral 0 to infinity fx dx if f is what? Even. Right? So if you have an even function, you just double your integral. And I apologize because I'm really using that fact here. So in other words, you can say, can I just know from the beginning that since you like using that 0 over that symmetric interval, I know it's a, it's not infinity, I just double this answer. That's the point I'm making. That to answer this question, that's the same as just doubling this integral from 0 to infinity. You say, why is that? Because this function here is what? Even. Okay, this is an even function. Go back to trig. I can share with you guys the even, this is kind of an interesting thing, because when I teach my trigonometry course, a lot of students, they're STEM students, right? They don't even like what? Even and odd functions. They go, oh, I hate them, even and odd. How do you prove it's even? How do you prove it's odd? That's like on their next test. Prove even and odd, and they don't like it. But if you know it's even and odd, doesn't that help you here? See what I mean? So, okay. So in other words, let's actually try to compute this because our function's even. What does it mean to be even? Excuse me. F of minus x equals what? F of x. What does it mean to be odd? F of minus x is minus f of x. So, so that's why when I look at this function here, I go, okay, that's a nice even function. So, okay. So remember, we have to integrate. That integral is going to be double 0 to infinity. What is that again? X squared 9 plus x to the 6 dx. Now, this is kind of similar to a question. This is similar to a question that was asked earlier between classes. I'm going to get my water. So how would you guys integrate this question? You got to use u sub. Okay, this is a nice u sub question. How do you do that? Go back and focus right in here. See this here? Here's what I know. Isn't that x to the 6? I can say, what can I say? Is that really x cubed to the second power? Can I replace that x to the 6 there with this? why does this work out so well? Do you guys know why it works out so well? Because what are you gonna let u be? Yeah. Why does it work out? Because when you differentiate, isn't that really what? Doesn't this term, this x squared term cancel? It's going to cancel here. See that x squared term up there? You guys see what I'm saying? When you find that dx will be du over 3x squared. So that integral, I'm going to keep the 2, though, in front. I'm going to keep that constant. I'm just going to bring it along. And I apologize to you guys because I'm kind of going out of this. Let me do this here. Sorry about that. Okay, I apologize. Let me move this out of the way. Here's my point. I need to write this as the limit as t goes to what? Infinity. 0 to t x squared. I have to do that first. And then now I can do what? I can focus on the integral. So I'm going to do the same exact steps, okay? What I'm going to say is I of t now. Let me get this here. Nine plus what? X q squared dx. Okay. All right. So again, I have x squared 9 plus really u squared. Dx is that du over 3x squared. So your x squared cancels. I end up with 1/3 integral 1 over u squared plus 9 du. Does anybody happen to know? And then this 9, isn't that really going to be 3 squared? So I'm not sure what color to use now here. Maybe green. What is this going to be? It's 1/3 inverse tangent of what? U over 3. Is that right? So all together, now in purple, 1/9, because I already had a factor. And what was u? Go back to the u, x cubed. And this has to be evaluated. My limits have to be from 0 to t. So it's 1/9 inverse tangent t cubed over 3. One-ninth. That's really going to be inverse tangent and 0 because 0 cubed is 0 divided by 3 is 0. And you guys know, what is this inverse tangent of 0 though? That's actually 0, right? So what you have really, now let's be careful because I think we left off a 2 factor. Is that right? So let's bring back that 2. Looks like it's 2/9 inverse tangent t cubed over 3. So what would you do with this now? Remember, what do we got to do with this integral? We don't know what it is yet. We got to take the limit now. I think I wrote it down somewhere. There it is. I put the factor inside 2. You say, Mr. Judge, what'd you do with that 2? We used it already, meaning I actually put it here. Right? Because limit of a constant is constant. I can pull out that factor too. All right, now we have to say this. What's going on here now, right? As t gets big, we didn't know what that inverse tangent t cubed over 3 goes to. Does anybody know where that goes to? Does this go to pi over 2? Do you guys remember the inverse tangent curve? Right? Isn't that limit pi over 2? T is getting big, so t cubed is getting even bigger, divided by 3. You're going to go to the inverse tangent curve. Doesn't it have a horizontal asymptote at pi over 2? Is that right? But don't forget, that means now the factor here, 2/9. So this portion is going to be 2/9 times pi over what? 2. Final answer is pi over what? 9. So ladies and gentlemen, this converges. That area equals pi over 9, wherever this is here. There we go. Let's get rid of that. And of course, that's a finite number, so that converges, right? Bless you. So that one converges, and that's kind of a nice question. I'm going to kind of look through my notes and maybe try to see if I could get one that doesn't converge so that you guys can see that there. Yes?
Question, Professor. Can you explain again how you got pi over 2 again?
Oh, why is that pi over 2?
Yeah.
It goes back to, remember we drew this picture here, right? The inverse tangent curve. You might even say, well, I don't even know. Well, how does that inverse tangent curve again? Remember that how the tangent curve looks?
Yeah.
That's pi over what? 2. Now this is tangent, so you can reflect this about the y equals x axis. So when I said this now has your vertical asymptotes are now what?
Pi over 2, negative pi over 2.
Yeah. So it goes back to the graphing, of inverse tangent. So this is actually t, and the limit's the y value. So all that's saying is if t gets big, t cubed over 3 is getting big. It's the same curve, which means the inverse tangent of that curve goes to pi over 2. Horizontal asymptote. And then again, already I've had a 2/9 factor, so the 2's cancel, and so it's pi over 9. It's kind of interesting. X cubed plus 9 over x to the 6th. Let's see what Desmos says. So x squared, I think. So you see how that's an even function? Can't even, I mean, I could change the y-axis, I guess. I could kind of fix what's going on. How come it doesn't like my finger? What am I doing? Anyway, that's a little bit better. So all I'm saying is the curves are, it's an even function like we said. Even functions are symmetric about the y-axis. So that's why you can get away with saying if this integral is over all real number lines, that's why you can say, hey, just double that area under that curve. Double that one. And you're going to get really for all real numbers because it's an even function. Meaning from negative infinity to positive infinity. Just double from 0 to infinity. That's what we just did. And we got a finite answer. That answer being pi over, 9. Okay, you guys okay with that? There it is, pi over 9. So I want to look at a situation where you don't get convergence here, where you actually get divergence. And so I'm going to look for my notes and go, okay, do you have something on that? And you guys remember, I do have what?